In this first review video, we'll look at some basic concepts that we began with the class. We started out by talking about the difference between analytic and algorithmic solutions. In your math classes and basic science classes, you often found the exact solution to a problem. An algorithmic solution is approximate, and we use some numerical procedures to do that. The procedure itself would be called the algorithm. So even if you have a problem and you do trial and error to try to find the answer, you're kind of doing an algorithm right there. Maybe not a formal one, but again, you'll find that you'll adjust how you do the trial and error as you get your results. Now, toward the end of the semester, we actually looked at both the bisection method and Newton's method for finding that solution a little closer, or finding formal methods rather of closing in. And we also looked at goal seek and solver with Excel that we use to find the solution. An advantage of algorithmic solution is that you can make a graph. And so understanding the solution or communicating the solution can often be helped out with a good graph. And also you can check your numerical solution. And in fact, you can check your analytic solution as well by creating a graph. So here's one where we looked at the projectile problem and we plotted height as a distance of x. In other words, this is what the trajectory of that projectile looks like. And again, it gives you information that you can visualize more so than just a table of numbers. So if we know, though, the exact solution to a problem, why would we ever want to use an algorithm? Well, a lot of engineering problems, there is no exact solution that exists. And other times it just may be very difficult to solve the problem. And in those cases, of course, an algorithmic solution gets you close. Other times you may have done the analytic solution, but it's a pretty difficult problem, and so you might want to, as a check, do an algorithmic solution to make sure that estimate you get off the algorithmic solution is close to your exact solution that you calculated. And again, the graphs really help in both understanding and communicating your solution. So we use two tools predominantly in this course. Won't emphasize this too much because you've had experience with both of them now. But we found Excel, if we just want to enter a formula and check it really quickly, then Excel was probably a faster way to do it. But the other thing is that because of the spreadsheet layout, all the calculations that you make, all the intermediate calculations, are displayed on the screen as well. If you have to use a lot of intervals to get to a solution, MATLAB's obviously a better choice. It's easy to change the number of intervals, and that way you can also tell if your algorithm is converging to a solution by using more and more intervals. So remember that what we call an exact solution is not necessarily the exact solution of a physical problem. Our mathematical model may contain a lot of assumptions. And so even if we solve that exactly, we may not be solving the physical problem exactly. So a couple of key points there. Again, a model is an approximation of a physical system, and that's what most engineering problems involve. An analytic solution gives you an exact solution, not to the physical problem, but to the model. And an algorithmic solution uses numerical methods to find that approximate solution. And again, it's good to use an algorithmic solution where it's hard to find or an analytic solution is unknown. And again, always remember that the exact solution is all dependent on what assumptions that you've put into it. Now, we also talked about independent and dependent variables, again, concepts that you've learned in your math classes. But especially when we start using programs like MATLAB, it's important to kind of use the terminology correctly. So an independent variable means that it's independent. It's free to take on any assigned value, and your dependent value is dependent on the value of the independent variable. Also a function. A function is a mathematical operation. For any input value or set of values, you get a single value back out. And in that projectile problem we looked at, if we said the independent variable was time, then we could calculate the height and the distance at each location. So looking at height in particular, height is a function of time. And so often we'll show that independent variable in parentheses. So there's our equation for height, and you can see h of t just means height as a function of time. And again, if we switch that around a little bit, well, actually say, what's the position x? Well, that would be a function of not only the time, but also of the launch angle. So in that case, again, we still get one answer. That's the key of being a function, but now it's a function of two independent variables. And finally, we talked about accurate and precision a little bit as well. In common language, we usually use those two almost interchangeably, but remember, accuracy is how close are we to the actual result. So we may have solved our mathematical model exactly, but our results may be way off. So accuracy, again, is how close are we, how close is our answer to an actual results. But precision, that's how exact are our calculations. So we could have calculated the landing position of the projectile to 8 decimal places, and we'd say that's a very precise calculation. But again, it may not be accurate. We looked a little bit about significant digits, and go through that pretty quickly because a lot of times we don't know what the significant digits of our inputs are. But if we're doing experimental work in the lab, then yeah, you try to follow those rules. And so if you have decimal points, the significant digits are defined as the number of digits between the first non-zero digit and the last digit. So in this case, there'd be 6 significant digits. 8 here. And if we lead with zeros, all those zeros don't count. So between the first non-zero digit and the last, this is only 2 significant digits. And 7. But when we get to engineering calculations, as I kind of alluded to earlier, we usually don't know how precise our input is. So again, projectile problem, we said 35 degrees, 10 meters per second as the initial velocity, but we really don't know how close those are to actual values. And so it's a good rule of thumb. We report our final answer usually to 3 significant digits. Some textbooks say that if the first significant digit is 1, you can go to 4. So 3 or 4 is a reasonable number. But if you want that final answer to be precise to 3 significant digits, remember to carry out your calculations to more than that and just round off at the end. So sometimes what you see students do is because of the computer will output 10 digits, they'll report those 10 digits. Again, that doesn't really mean the answer is that precise. Excel and MATLAB carry through 15 digits usually in most of the operations. So again, always round off when you get to the end. So a few important things here about that. Remember what a function is, and that becomes important later on when we start using MATLAB functions. Report your final answers to 3 significant digits, maybe 4. And also remember that if you are going to report to 3 or 4 significant digits at the end, don't round off to 1 or 2 on your intermediate calculations. And next time we'll start talking about Excel in more detail.